take us to a place with as little gravity as we can find. Now imagine that you're in an elevator at the center of this great void. You're not accelerating. You're weightless in an inertial frame, stuck to the bottom with Velcro boots. You're holding a ball. If you let go, it would float in place. Now imagine that the elevator starts accelerating at a constant rate. You will now feel a force pulling you down. Let go of the ball again. This time, it falls to your feet. No matter where you let go of the ball, it will feel the same force and fall to the bottom of the elevator. In other words, at every point in space inside the elevator, a force is felt. This is a force field. The elevator's acceleration has created a force field inside the elevator. The acceleration of the ball follows Newton's second law of motion, that force equals mass times acceleration. Now turn off the engines to return to an inertial frame. You're not accelerating. It's dark. You turn on a flashlight and watch the light reflect off the far elevator wall. Start the elevator accelerating again at a constant rate. Turn on your flashlight and watch the light beam hit the far wall further down than it did when you were at rest. The light bends down. Now let's take a look at what a person outside the elevator looking in would see when we drop a ball and shine a light. The person outside the elevator is not accelerating. When the person in the elevator lets go of the ball, the person outside the elevator sees that it still hovers in place, just as before. He sees that the elevator moved up to hit the ball. There is no force acting on the ball. There is no force field inside the elevator. And when the person in the elevator turns on the flashlight, the person outside the elevator sees the light travel in a straight line as before. He sees that it's the elevator's wall moving up that causes the light to hit it at a lower point. The light does not bend. Who is right? Before Einstein's general theory of relativity, we would have said the inertial observer was correct, and the person in the elevator was fooled into thinking he is in a gravitational field. But according to general relativity, they are both right in their own reference frame. Gravitational forces have materialized for the person in the elevator due to its accelerated motion. According to general relativity, this gravitational field is as real as one created by the existence of a massive object. To see this, let's compare what the person in the elevator is experiencing and what a person at rest in a gravitational field would experience. We know that Earth's gravity near the surface accelerates objects at 9.8 meters per second squared. If we set the acceleration of the elevator to 9.8 meters per second, the occupant would experience the weight he feels on Earth, and the ball would fall at the same rate as it does on Earth. In fact, the person in the elevator cannot tell the difference between the two situations. Is he out in space being accelerated by some force, or is he at rest on Earth being accelerated by Earth's gravity? As far as the laws of physics are concerned, being accelerated and sitting still in a uniform gravitational field are equivalent. This is Einstein's general relativity equivalence principle. It is a generalization of special relativity that holds that the laws of physics were the same for all inertial reference frames. With general relativity, we hold that the laws of physics are the same for all reference frames, no matter what their relative motion. The equivalence principle has a number of implications. One of the most significant for us is that it tells us that because light bends in the elevator, it will bend in a matter-generated gravitational field as well. You'll recall from our segment on special relativity that light speed in a vacuum, being a constant, led directly to time dilation, space contraction, unusual velocity addition, and the end of simultaneity. With general relativity, we'll see how the bending of light in a gravitational field has its own set of even more dramatic changes to our understanding of the physical world.